Alright, so in this video I'm just going to finish off with these practice questions on topic 2, the electric flux and Gauss's law. So, two infinite sheets, uniform density, plus and minus density, are parallel to each other as shown in this picture here. Okay, so we have a field lines going like that in between them, and there is a formula for two infinite sheets. It's well, actually that, you just remove the two. Let's get on with it. Midpoint between the sheets is 0. Well, no, because there's maximum in between, so that's wrong. Points to the left or the right is 0. Well, yeah, actually, over here and over here, they will cancel. It becomes 0. That is true. Midpoint is the density over epsilon. That is correct, and this one is wrong. Or if you remember why, we derived it in the lesson video in the PowerPoint. For one sheet was density. What am I looking for again? Density over 2e. That's for one. If I had two, I'll do density over 2e plus density over 2e, epsilon naught. That's a half plus a half, density over epsilon naught. It's more clear in the video if you want to go back and watch that. Sorry I keep referring you to it. I just don't want to bog down this one going through things that I have already explained. So directly the answer here is 2 and 3 only. There we go. These two, this one and this one. A charge is placed here in the center. What's happening about the field? So this is a negative charge, so the field line actually comes inwards. It's coming towards it. A inwards, C inwards, B is inside the shell. That means it's 0, it's cancelled. So it is inwards at A and C and 0 at B. This is good. This says 0 at B and C, so that's wrong. Inwards at A, B and C, wrong, because B, no. And outwards, wrong. Directly, the answer must be B. Okay. Which of the following statements is false regarding a conducting sphere? So let's find out. Inside the charge or neutral conducting sphere, the electric field is 0. Yes, because in the sphere, if it's a conductor, the charges will point and run away to the edges. Inside E is 0. Inside the conducting sphere. This is true. Even a hollow insulating sphere or a hollow solid sphere, solid doesn't make sense. A hollow conducting sphere, same answer. A hollow insulating sphere, same answer. Why? Because they have to be there. They have no other place to be. There's nothing inside. It's just empty space inside. So each case it is 0. The only time it's not 0 is if it's a solid insulating sphere. That's the only time we have to deal with something which is not coming up here, which is nice for you. Okay, done. There is no, what have I done? Have I got the answer? No, this is correct. We're trying to find which one's false. Okay. There is no net charge inside the sphere. Well, yes, we agree. There's no net charge. I could have a -1 and a +1, and they will cancel, so it'll be 0 again anyway. So that is also fine. The potential, the V, is constant throughout the volume, so it's equipotential, which is true, because the potential is the same everywhere. The charge is the same everywhere. The electric field at the surface must be tangential to the surface. Tangent means like if you have a circle, the tangent kind of goes off in a line like that. That is a tangent. That's wrong. It goes out. It's perpendicular. It is not tangential. This is the answer. All right. You probably don't want to put ticks there because the teacher might think that you have ticked them all. There you go. Right? That's better. You could probably put an X there because we know that this one is wrong. Or you could just put a little tick here. Whatever. Okay, what am I doing? Let's move on. Next question. 69. The electric field for R inside the big R1. So the question says we have a plus Q uniformly distributed. We have a plus Q all the way around here. It looks like there is nothing inside it. So if I have my R smaller than R1, so that will just be here, somewhere along this area here, there is no Q enclosed. The electric field inside is 0. The electric field R greater than R2. The R being greater than R2. So that's somewhere out here. Somewhere out here, the electric field, there will be. The enclosed charge is here. We have Q right there. So E, or outside, is directly, just using Coulomb's law, KQ over R squared. Electric field, we square it. And that will just be, well, the K is not here, but we do know that K is the same as 1 over 4 pi epsilon naught. That is also K. So I could write it out as 1 over 4 pi epsilon naught multiplied by Q, and it's just a positive Q over, and what is my radius going to be? It is from the center. It's just basically R, just going to be R cubed. We assume it is a point source. We just assume it's from the center. Even though there's a difference in the radius, not important. We'll take it from the center. Okay. Okay, so that's the rule over here. So from that, I can get the answer of C. Another way to do it is by deriving it. You can just use the derivation. So E A equals Q enclosed over epsilon naught. We're talking about this part over here. And then you can rearrange the formula to get E. Of course, A, the area of a sphere, is AE multiplied by the area, 4 pi r squared equals Q over epsilon naught. And what I'm going to do now is just rearrange it to get E. E equals, and I'm going to take that to the side, Q over 4 pi epsilon naught. Well, I've got the r squared as well. Rearranging that or shuffling it around, it'll look just like this one here. It'll look just like that. There's an imaginary one at the top. Okay, very nice. Oh, and that's it. We're done. That was easy. That was a short video.